Okay, let's do this.
Last time, we looked at something called an Euler equation. So let's talk about the Euler one where we don't need cosine. What does that look like?
Alpha n minus n1, n minus 1 n.
Is it
No.
alpha x squared plus beta x y prime plus the gamma of y?
It's on top of it. It's on top of it. Okay. So obviously here your alpha is not equal to 0. That's called an Euler equation. How do you solve it?
Initial equation.
Right. You assume y equals x to the r. This leads to something called an addition equation, which looks like
Alpha r minus r1,
r times r minus 1 plus
beta r.
r plus gamma equals 0. And you can solve and get a bunch of roots from that. So we have two real distinct roots. What does our solution look like?
C1 x to the r1, C2 x to the r2. But you have to check if their r is less than 0, or x is less than 0, and then you put absolute.
Yes, so here we're assuming x is not equal to 0. If it's less than 0, you put the absolute values, and let's assume it's greater than 0. What about if we have one real root, our repeated roots? Looks like
C1 x to the r, C2 x to the r, natural log of x.
x, and we have r equals complex roots, a plus or minus, I.
C1 x to the r, x to the a, cosine b,
Cosine
natural log of x.
b ln x plus c2 x to the a sine x. Okay. Now we learn how to solve those. Those are just another type of equation that's, in some sense, very similar to if we have constant coefficients, because there's a very standard formula that breaks into three situations, and you should just know the formula, know the three situations, and you're good. There were other guys, though, that were a little bit sketchier. So we also looked at more generally e of x y double prime plus e of x y prime plus r x y equals 0 at points where x naught where p of x equals 0, such points were called not necessarily regular. So x is called a singular point here. And pretty much we divide it through by p, we multiply it through by x squared, and we kind of shift things around so that we can get these guys to look kind of like the quadratic form that was above there. And we kind of pretty much assume that there is a way, there exists some power series solution such that all the terms that makes it not look like that will all vanish to 0 as we approach infinity. And if such a thing exists, this guy we can say kind of behaves like an Euler equation, and so we can actually have a series solution there that looks like a reduction of order kind of thing, x to the r times some power series. So that was the assumption. I don't think we actually did an example, so
We talked about finding regular.
yeah. So we say x naught is a regular singular point. If what happens?
P of 0 is like limit as x equals x r, which is x minus x naught. Q over p is finite.
Q over P, because I'm dividing P by that.
It's finite.
And you want two limits to be finite. The other one is
R over p. X minus x naught.
Square.
Oh yes,
x minus x naught squared are finite. Otherwise, x naught is an irregular singular point. And we won't deal with these, so you can kind of ignore that case. Won't deal with these. So we're only going to focus on the regular ones and actually one particular situation in the regular ones even. So yeah, so we have another equation and we know how to solve that. It is one of the simplest kinds of differential equations where the coefficients are non-constants that we have a really nice way of solving. So if we generalize this to non-constant coefficients, we're saying, hey, maybe we can force it to look like an Euler equation. And this, if these work out, then it feels like it should be possible, and we should be able to find a power series solution to this equation. Now, of course, if that's not possible, then you have to just try something else. But there are many times in which it is possible, and in this class, there are going to be situations in which it is possible, and you're going to actually just find an equation. Find a power series solution. So now, if x naught is regular, we assume a solution of the form. Right, we're going to look at it like x to the r times some power series function. So like a reduction of order kind of thing. We think of it as a solution times some other function that we can find that other function, and we assume that that other function is going to look like some power series. More generally. Or, in other words, we want a power series solution that looks like that. X naught to the n plus r. Now, I don't believe we got here, but every now and then we can actually solve for a solution like this. And I want you to appreciate that the r here is going to be the r that if this guy behaved like an Euler, that would be the r. So,
The R is no way.
we want this guy to behave like an Euler equation, even though it's not an Euler equation. So,
But it's the R from the initial.
that is the R from the initial. Yeah. So now, how do we actually make sure that happens? Well, remember how we kind of set this up? We kind of wanted, basically what we did was we divided through by p and multiplied by x squared. And so here I can take an x times, like an x times p over q. Now of course I can x minus x not, but I just can't do it.
Q over p.
Okay. Plus I can multiply this by r. We have this guy, right? So basically what I want is like, what?
Q over p.
R over P.
Why did I keep Q over P?
And R over p.
R over P. I divide through by P, and then I multiply across by x naught. I push in one of the factors here, I push in both factors there, and basically my idea is I'm hoping that this guy behaves as if he's a beta. And this guy behaves as if he's a gamma, right? So I'm thinking, okay, I want in power series form, as I go off till the power goes off to infinity, the power series of whatever that is going to behave like it's a constant, and the power series of whatever that is going to behave like it's a constant, which is why I need these limits to actually give me finite numbers. Now, in the event that they do behave like constants, I would be able to find an initial equation to this weird Euler equation. So this means R should satisfy well, it's going to be like my R minus R1 plus, call this P little r, P naught, that's the standard notation, and Q naught equals 0, where I call this one P naught, and I call that one Q naught. Because it kind of looks like the alpha r minus 1 plus beta, which I'm assuming that this guy is going to look like beta in the limit, which is that P naught, plus gamma equals 0. And I'm going to assume that this guy looks like gamma in the series form, which approaches Q naught. So we say that P y double prime plus Q y prime plus R y equals 0 has an associated Euler equation, and so basically we're going to think of this power series as behaving similar to an Euler equation that has these guys as the constants, and the above is its initial equation.
So like you always say, we're just guessing, happy if it works,
Yep.
and then that's it.
And if it works out, EUT takes over. I'm like, hey, I guess that's the guy. So we have that, and so pretty much I can assume a solution looks like this. I can figure out what the R value I have to plug in, because remember our solution typically depends on n. We have to find the an and blah, blah, blah. So that part we kind of know how to deal with. There's just going to be an extra term here, like a plus R, which in one sense you can think of us actually trying to make it look like another. In another sense, you can just like shift it a little bit. You got it. Can I find an R that makes that work? And then pretty much the R that I just threw in there must satisfy this equation, because I'm trying to get it to behave like a type of equation that I know how it behaves.
So the R is the stipulation that's going to allow us to choose the correct n.
Yeah, well, yes. It would be, I want to choose an R value so that it actually does behave similar to an Euler equation in the series form.
So R is a guess.
Well, it's not even a guess. We can actually know exactly what it is. Like, if these two guys actually work out, they will give us numbers. I'm literally going to put that number here and here, and I can actually solve for the R.
Are we going to have 2 R's?
You will have 2 R's. In general, you have 2 R's. There's a case where, with the power series, it actually gets a little bit more complicated. In general, you'll have either 2 R's or a repeated root. So, the complex situation is going to give you some complex series. We're not going to deal with that. If we have real roots, a repeated root, there's going to be a modification that you have to do to find the second solution. Is like you're going to have to put in the series of ln somewhere so to make it behave like what I erased. The only case that we're going to deal with is distinct roots. So every problem I ask you here is going to have distinct roots. And pretty much there's a theorem in the book that tells you like a formula to do with the other cases, but we're not going to do it. If you're interested, you can read it. And there's even, to be a little more complicated, there's a situation in which if the roots, the 2 R values are an integer distance apart, you kind of have to manipulate the solution differently from if they're not an integer distance apart. We're not going to worry about that. Basically what we're going to do is I'm going to, hey, here's a differential equation. Find a series solution near the regular singular point. You're going to figure all this out, and then I'm going to ask you, find the solution corresponding to the larger root. And then it's pretty much going to be like, from there you follow your nose with the series solution. That's going to be that. That's the one case we're going to deal with. The other cases, it's similar, but there are some little nuances that you have to make some changes that I'm just not going to bother with. So, that being said, let's actually do some equations. actually practice setting this guy up. So what I'm going to want you to do is show x equals 0 is a regular singular point. And find the initial equation for the associated pair. A. X squared y double prime plus x y prime plus x squared minus 1 over 9 y equals 0. X y double prime plus y equals 0. Two x y double prime plus y prime plus xy equals 0. Now all of these are an easy case where there's going to be a nice little trick. I'm going to show you that will work, where you don't even have to be as general as I'm telling you up there. So oftentimes a problem like this is going to be somewhat annoying, even more annoying than a series problem typically is. So you'll have a problem like this and it'll say, oh, show that this is a regular singular point, or find all singular points, show that one is regular, show that the others are irregular or whatever. Find a series solution at near the regular singular point, and then you're going to have to kind of go through this in the beginning, and then you wrap it up. But let's actually just get to the start. Let's actually just try to get to that equation so we can actually figure out what R value we're going to pick when you're actually choosing a series solution. So, A.
You divide through by x squared.
Sure. Here we have, what is this, 1 over x, y prime plus
1 minus 1 minus x squared.
And so, obviously 0 is a singular point because it makes this discontinuous. Also it makes that discontinuous. How do I know it's regular?
There was a test for that, right?
Yeah. Yes.
Well, R over P should be finite, so 1 over x as x, 1 as x equals x naught.
The limit at, what is our x naught here?
Uh,
So this tells you that x equals 0 is a singular point. How do I know that it's regular?
X naught
Yeah,
should be 0
it is 0. So I'm going to take the limit as x squared is 0. Up.
of 1 over 0. Would it be x minus 0 and then
X minus x naught times
1 over x?
this guy.
Then use loop.
Now what's that going to give you?
It's going to give us x over x, which is 1.
1, which is good. Okay, so we're going to find the next limit. So this here would be our P naught.
What's the test scaling would look like? It would just be 0.
Like, no, it would be non-finite. So you either get infinity or does not
Oh,
exist.
okay, I got it.
Limit, this one is x minus 0 squared times 1 minus 1 over 9x squared. What is that going to look like?
That would be x squared over 1 minus 9, x squared minus 1 over 9, which is this. This is continuous. It's just negative 1 over 9.
Minus 1 over 9. I can call that my q naught, which these are both finite, so that's regular. X equals 0 is regular. Okay, now that I know that it's regular, find the initial equation for the associated Euler.
So now during this step, we're making it so that we know that we can treat the P
We can treat this
as another
thing
equation.
as a kind of degenerate Euler equation, if you might call it. It's one that we can't really use the x to the r situation to solve, but we can use a power series to solve in the form that I mentioned before. And so it's going to be a series of an times x to the n plus r, but what is the r? How am I going to find the r?
Use the initial equation on the
Right, which is?
r minus 1 r
Plus 1
r
r
negative 1 over 9.
negative 1 over 9 equals 0. That's going to be the equation. So this 1 and this minus 1 over 9 comes from this 1 and this minus 1 over 9. So now that's my quadratic. I want to solve for this. So this is 9r squared minus 9r plus 9r minus 1 equals 0. That goes away.
Wait, where does 9 come from?
I multiplied 3 by 9 to get rid of this fraction. So that's a 9 here. That gets to be a 9. That gets to be a 1. So this gives us what?
R is equal to 1/3 and plus or minus 1/3.
Right, so 9r squared minus 1 equals 0. So this is 3r minus 1 times 3r plus 1. And so equals 0, which means we have two roots here. R is equal to 1/3 or R is equal to minus 1/3. I mean, it only said find the initial equation. It didn't really say solve it. But if you wanted to do the problem, you would actually solve it. So you are going to go into the series solution and you would plug in 1/3, for example. Yes.
So when we found the standard form of this, we needed to have x squared in front of y double prime.
Yeah.
Which we do in this particular case.
Yes.
But then we divided by the x squared as if it was the p of x. And when we found the standard form originally, we had p of x y double prime, q of x y prime plus r of x y. We divided by p of x, and we multiplied everything through by x squared.
Yes.
So if we did that, and we divided everything by x squared, and then multiplied everything through by x squared,
Yeah.
and we back at the initial equation, which then changes.
Well, yes,
here.
but the reason why we divided through by x squared is to figure out what I should have in this portion here and this portion here.
I thought we could only establish what beta and gamma were once we had an x squared in front of a y double prime. So we don't want to have anything in front of a y double prime?
Yes, but to actually factor it from there, it's easier to see here because you just take this and put it in this position, take this and put it in that position. But technically, yes, you would put an x squared here, you would have an x times an x here, and then you would have an x squared times that, which this whole thing with the green is actually what's here. And this whole thing with the green is actually what's here.
Right, so we're just sort of skipping that step.
Yeah, we're sort of skipping that stuff.
Okay.
We like to divide through by x so that we can just say, okay, it's going to be x minus x naught times blah. What is that blah? It's going to be that guy we get when we put it in standard form.
Okay.
Yeah. Yes.
I know we weren't taking it that far, but if we were asked to solve what's y equal to just the real distinct roots, c1 x to the r1 plus
No,
x to
that won't work here because it's actually not an Euler equation.
Okay.
So to actually go further, you actually need series.
Oh,
So to actually pull this all the way, we're going to do a n x minus x naught to the n plus r, where I'm going to actually plug in for the r 1/3. And then I go through series.
Does it matter if I plug in positive or negative 1/3?
I'm usually going to ask you to do one of them, the larger root. Because to find the smaller root, you have to kind of tweak things a little bit, and if they differ by a constant, which these guys do, you have to tweak something a little bit further. But I'm just going to say, okay, find the initial equation, find the solution corresponding to the larger root. In this case, that would be 1/3, and you really just put in 1/3 and find the answer was 1/3.
So then you're basically starting from the beginning of doing a series solution
Yes,
with that new series.
with the new series, yeah.
What we've been using.
Yes, but we have to get to a point where we know what we need to shift things by in order to even start that series solution.
So this is like half the problem.
This is
A
7.
quarter.
Yeah.
Something like that, yeah.
1/3.
1/3. Here's a shortcut though. Because, yeah, we did kind of seem like we're dividing by x squared, and kind of technically we're multiplying by, here's a shortcut. Let's say you can get the first term to behave, right? So let's say you have alpha x squared y double prime plus, you have a beta, well, not even beta, just forget it. Let's say you have some other random function, whatever I want to call it.
Yeah, smiley face.
Smile bit. I don't know, big P. No.
WZ should be kind of small, makes the.
W X Y. No, because Wronskian has more than one argument. I don't know. N. Right? So let's say I could get the first guy to be like an x squared, meaning divide through by whatever was here, and then multiply it through by x squared, right? And this is just a new guy I'm looking at that has that form. Here's how you can get to the initial equation. Then, which you're not always going to be able to do this, at least not in a nice way. However, this class in 391, I'm also going to give you one where you can kind of always do this. So in general, you have to do that r times r minus 1 plus p naught r plus q naught equals 0. That's how you know you're not making a mistake or whatever. But there's a shortcut sometimes. If you can get the first term to behave, then all you have to do is make sure everyone else falls in line, and you can actually get to things a lot quicker. Then the initial equation will have the form alpha r minus 1 plus beta 1 r plus gamma 1 equals 0. Where beta 1 and gamma 1 are the parts of W and N by Euler terms. Ignore the others. Okay, so let me explain well, let me show you what I mean by that. So looking at A, again. Notice that the first term is actually in nice form. He's in funny form for me. Which means, I just need to make sure these two guys are behaving themselves. Now, what should the beta term look like? Well, it's a constant term times an x. This already is a constant term times an x. So that actually has a nice form. Here, then, my beta 1 is just 1, because that would be the constant. Now, if I go over here, Who's in good form? Well, not the x squared. To be an Euler, what do I want here?
Oh, nothing.
I want just a constant,
Minus 1.
which means who's messing up?
The x squared.
The x squared. Messed up the form. Go and you cut him out, right? It's like, yo, you're messing up the form, dude. The minus 1/9 though does actually fit the form. He's a constant, so gamma 1 equals minus 1/9.
Oh, all right.
And now, what would the equation look like? Now you just think of that as the beta and that as the gamma in r times r minus 1 plus beta times r plus gamma equals 0, which happens to be
That's up there.
I ended up right back where. So pretty much fix the first guy, ignoring one who breaks the form, and that's my Euler initial equation right there.
Can more than one break the form?
Yes. You just ignore whatever part doesn't fit the form. So let's. Yeah. The first one didn't need to be fixed. He was already in the x squared form. He already looked like alpha x squared.
Yeah.
So I want it to look like alpha x squared plus beta x plus gamma, right? Where beta is constant, gamma is a constant. Now, this guy looks nice. He looks like an alpha x squared. Awesome. This guy also looks nice. He looks like a beta x. Awesome. This guy, though, he should look like a constant, and he doesn't look like a constant. What's messing it up? The x squared is messing it up. Ignore the x squared.
So can you show us one with an alpha that's not
I think B is gonna be different.
Come again?
I said use that same method. You gotta do lower response.
We're going to do B. We're going to do B. We're going to make sure that you get what I'm saying. Now, to be fair, this way of looking at it is not sanctioned. So, if you're talking to a math person, do not say something like this. Definitely don't tell them Jhevon said it. Definitely don't say that. But if you're talking about an engineer, you'd be like, yeah, Jhevon showed me this cool trick, man. Right? Engineers love that stuff. Mathematicians, well, what's the theoretical basis for it? Like, dude, it's just when you turn it into a power series, what's going to happen is the parts that don't fit will fall out. We assume that in the power series form, they just go off to 0. So I can essentially just imagine that everything that breaks the form goes to 0. And I just keep everything that keeps the form. So if I look at B, what do you think here?
Multiply by x.
Multiply by x.
Also, we just want to choose something to make sure that the beginning does look like x squared.
Yeah,
So we're not always multiplying through by x squared.
No, I just wanted to start looking like what it should look like. So, in other words, I can think of this as x squared y double prime plus 0xy plus xy equals 0. Okay, who fits the form?
Isn't it 0 x y prime?
Yeah.
Right, so like my beta is 0. So first of all, it's my alpha r minus 1 plus my beta times r plus, who's gamma?
1.
No, it should be 0 because x doesn't fit.
It's 0. X does not fit the form. It needs to be a constant. So get rid of it, ignore it. So that's all. Just leave it there. So your r equals 0 or your r equals 1. Let's do it.
That's supposed to be a y prime, right? The 0 x y?
Yes.
I just wanted to make sure I was screwing up.
Would you get the?
What would you do with this?
You just multiplied by x.
Multiply by
Multiply by x. Were you asking the question? Or were you?
Yeah, no, that's. So I guess that's what it is. Yeah, you're just
Like, the time was perfect. So you just multiply by x. I think he was asking a question over there, and it happened to be what I should be doing over here. So that was, yeah, the time was perfect for that. Multiply by x. Yes, you multiply by x.
That's what we're doing.
Why would you multiply by x? To get this guy to look like alpha x squared. Now, in that case, what would my beta be?
1.
1.
1. What would my gamma 1 be? 0. Because that guy messes up. He's not a constant. He should be a constant. So pretty much now I have 2r, r minus 1 plus beta r equals 0. And I have 2r squared minus 2r plus r. So I have r times 2r minus 1 equals 0, so my r equals 0, or my r equals half. So yeah, you could go through and find the limits, here's Q naught, here's Q naught, and then you come and you plug them in, but you can also kind of eyeball it. That's the engineer way.
Wait, so if r is 0, that means the point that we're at, where x value is 0, or if you did the power series solution and r is 0, would that mean that the point we're at is a regular?
Well, this is going to be regular either way. I mean, we didn't prove that it's regular, but x equals 0 would be regular. And it means that there's an Euler series where you can plug in the series a n x to the n plus 0 and a n x to the n plus a half. And these should give you a series solutions. Let's look at those. D. Okay, quick, someone tell me the answer to this.
R equals 0.
Tell me the initial equation.
X squared y prime plus 1.
No, the initial equation is the guy with the r's.
Oh.
Bring it to this level.
1 r minus r,
R times
Do you multiply everything by x?
r squared minus r plus. We can't do it in our head.
I didn't ask you to do it in your head. I said just do it and tell me the answer.
Plus
Say it in your head. Work it out quickly. I said do it quickly, no? Doesn't always mean in your head.
Can't be sounding like that.
Just wanted you to do it before I do it, so I know if you're following. Do both of them. Just get to the initial equation, this equation right here.
R squared is equal to 0,
Yeah.
For this one, you get r squared.
is equal to 0.
What about this one?
Get,
Squared minus 4r plus 3.
Let's see for D. What did you do?
Multiply by
Multiply by x squared, or by x, it will give you x squared here, this will give you x minus x squared, y prime, and this will give you minus xy equals 0. So, that's an x squared. Who messes up here?
That guy.
x squared
X squared messes up. Who
and the
messes up
x,
here?
b minus x.
That whole thing. So, I just have r minus 1. The coefficient here is 1. So that's going to be plus 1 r, because that guy fits. No one here fits, so I end the equation. R squared minus r plus r equals 0, so we have r squared equals 0. So that's the correct equation. We have a repeated root of 0. Which means that if you were to do that limit to test whether it was a singular point, you would get that the first limit will give you 1 as the answer, the second limit would actually give you 0 as the answer. So E. So this here is x squared y double prime minus,
X squared minus.
it will be minus 3x squared, y prime plus x plus 3y equals 0. Okay, who messes up?
Minus
Minus
x
x
squared.
Minus x squared messes up. Who messes up here?
Here, plus x.
The x messes up. Everyone else fits the form. That's going to be like my beta.
And then gamma 3.
That's like my beta 1 here. And then my gamma is actually, gamma 1 is 3. So I pretty much pretend these guys aren't there. Just like I don't even know them anymore. They're dead to me. So I'm pretty much looking like this is the Euler equation. And then I'm going to set up the equation based on that.
Why is it beta 1 and gamma 1?
Because I don't want, it's not a real beta and gamma from the original form. Because there's a thing.
Oh, okay, so like beta prime kind of.
Yeah, like a beta. But, you know, we're in differential equations. The prime already means
Yeah,
something.
that's true.
So, minus 3r plus 3 equals 0 would be this one. That's r squared minus r minus 3r. That's r squared minus 4r plus 3 equals 0. And that's
R minus 1, R minus 2.
so either r is equal to 1 or r equals 3 are the roots. So, let's actually bring one of these to fruition. Here's another thing. Sometimes you're asked to find what the roots are to the initial equation beforehand, but it turns out that you don't even really need to know that beforehand if you kind of go with the method where we pay attention to what the indexes are. If you don't pay attention to the index, then you should be finding this separately.
Oh, right, because we have that other method where we're...
We have that other method where we can go all the way down to negative infinity and just not worry about indexes when we're shifting indices. So maybe I would do one when...
Didn't you say we were gonna have a problem when r was an integer?
Or the difference between R.
When the difference between ours is an integer, there's a way that you have to do things to get the general solution, but I'm not going to ask you to find the general solution. I'm going to ask you to find one solution, one of the two independent solutions corresponding to the larger root. So, example. I think x, y double prime plus y equals 0. X equals 0 is a singular point. I'm going to verify that. Find a series solution near x equals 0 corresponding to the larger root. The associated Euler's initial equation. So I gave you that. It's the first thing. Yes. Okay. So here's the thing. Once they tell you, or once you know, they have you figure out x naught, x equals 0 is a singular point, and they ask you find a series solution near x naught. Together, that kind of tells you this isn't a regular series solution problem. This is a solution where you're going to assume your y equals a series of a n x to the n plus r. That makes it different from what we were doing in the previous series section. So if you're doing a series solution near a singular point, you need the n plus r. Now that also has a few consequences if we're actually paying attention to the indices. If we're not, it doesn't have any consequences whatsoever. But if we're paying attention to the indices, this automatically has consequences because this would mean that my y prime would look like what?
N plus R.
N plus r, a n, x to the n plus r minus 1. Now here's one thing that is going to be different. I cannot actually move the index. You should notice that that's true. That this has to stay at 0. I can't bump it up to 1 like I could before. Why not? Because if I plug in n equals 0, I'm not guaranteed to get 0 here because the r is going to save that term. So it's not like he gets wiped out at n equals 0. So I can't actually bump up the index like I did before. So that's something you have to worry about. So in this form for the series solution, once I start taking derivatives, the indices do not bump up. They have to stay situated at 0. So it's going to look like n plus r times n plus r minus 1 a n x to the n plus r minus 2. So pay attention, if you're paying attention to the indices, they don't get bumped up upon taking derivatives. Whereas in the previous situation, I could bump them up. So that's the first one. And again, like in the previous series situation, I don't expect you to actually write out this part. I expect you to kind of see that in your head and just immediately jump into plugging in the series form into that. Another pro tip, so that you don't get like negative subscripts and start getting confused, if negative subscripts would confuse you, is to, once you're getting the series solution, you probably want to actually fix it to look kind of like an Euler in the first place. So I would actually still multiply through by x, and I'm going to use this equation instead. And now, so what's going to happen if I plug in y double prime, that series here, the 2 is going to kill that negative 2 right here. And so the first one is going to look like n plus r, n plus r minus 1, x to the n plus r. Plus, here we're going to have x times the y. So it actually becomes an x to the n plus r plus 1 equals 0 to infinity. Now, I'm not in a situation where I can just shift indices without at will here anymore because making n 0 doesn't actually kill anyone. So, or making n 1 isn't going to kill anyone. So I'm kind of in this situation where to fix this, I'm going to have to shift it. Shift all n's to n minus 1, so this guy is going to start at 1. And in order to get this guy to start at 1, because I can't just bump him up to 1 without worrying about it, because there's the r there that's going to...
Before we go on, could you explain the n plus r plus 1?
Y is equal to a n x to the n plus r. I have x times y, that x comes in, adds 1 to the power. So I have this. I want it to look like the power n plus r, so right here I'm going to do a shift all n's to n minus 1s. This becomes n minus 1, so I can add 1 to both sides to start at 1. This becomes n minus 1, that becomes n minus 1, which kills that one, and I have this. This guy I didn't do anything with. However, he is now at 0 while that guy is at 1, which means to get them to start at the same point, I'm going to evaluate one term here. What is that term going to look like?
A of 0, r minus 1. To the n, x to the r.
And then I can start everyone at 1. Now, here we're going to have a n plus r minus 1 plus a n minus 1 x to the n plus r equals 0. And what we're going to do is we're going to set each coefficient equal to 0. Set equal to 0. And I'm going to set this equal to 0. Now I want you to notice what the first one would give us.
Does that mean we're not assuming that x to the n plus r can ever be 0?
We're assuming that the x is non-zero. Yeah.
All right.
We want this to be 0 regardless of x, so really we can only force the coefficient to be 0. So all the coefficients need to be 0 because we need to add it to a 0 series. This means, of course, your a0 r times r minus 1 must be 0. It also means that this guy must be 0, in which case I would solve for the an. That would be minus an minus 1 all over
N plus R,
n plus r.
What was the second one that you assumed was 0?
N plus r minus 1, the second one.
Oh, that's, okay, I see it.
Yeah, because that's an x here. So I'm just going to assume all the coefficients are 0. But hold on, here. So A0 is what? We have no control over that, right? That's going to be the initial condition. So if this should be 0, what's going to happen? This part has to be 0, right?
Oh, that's based off of what our singular point was?
Must have r times r minus 1 equals 0. Okay? So, if you start to do this guy and you want to get all series to be the same, you're going to evaluate a bunch of terms. Some of those terms are going to end up being the coefficients of x to the r. What you're going to notice when you take the coefficients of x to the r, what does that look like? That's actually the initial. So they kind of pop out anyway, right? As long as I'm paying attention to the subscripts, that is. So you can actually do a double check. So, which means, had I done this process on that, eventually I would evaluate a bunch of terms to try to get all the series to start at the same point. When I look at the coefficients of the x and the r's for all those terms, it's going to end up being this guy, times like A0 or whatever. And then that equation is going to come back, like I'm going to see it again, right? So you have the option of either finding this guy separately and then not having to even worry about this, just because it doesn't matter what the subscripts are, I'm not going to evaluate anything. So I can just find that separately and know that that's what I'm going to use to find the r, or I can pay attention to the subscripts and I'm going to figure out that guy anyway. There's going to come a point where I'm going to have to set something equal to 0, which is going to end up being exactly what that equation is. Other than that, nothing else really changes here. We're just going to use this to find the coefficients. Now, what you're going to notice is we want a solution for larger root. What was the larger root here?
1.
R equals 1. So I'm going to pretty much go here and plug in r equals 1. I use an equals minus an minus 1 over n plus 1 n plus times n. And now I'm just going to find a bunch of coefficients. So, A0 is just A0. You'll notice here that your A0, according to this, would be 0, because you're, if I plug in 0 here, I would get a to the minus 1 there, which is not a part of our series.
Does that just mean all of them come to afterwards?
Well, we don't know.
Yeah, that's also good. Because the numerator is A0.
Yeah, we already established that A0 is 0. Right?
No, A0 we actually don't know. A0 is given. So A1 is going to be, well, A0 over 2. A2 is going to be minus A1 over 6, which is going to be positive A0 over, A3 is going to be, plug in 3 for n, minus A2 over 12. This is going to be, if I plug in A2, minus A0 over 144. Yeah, that's not a nice pattern, so let's just stop there. At least I don't see a nice pattern. What would the next one be? A4 would be minus A3 over, that's 4 times 5, that's 20, equals positive A0 over 20 times 44, 144. That's not anything nice, is it? I mean, that's 2. This here is 2 times 2 times 3. This here would be 2 squared times 2 squared times 3 squared.
Oh, wow.
This here would be 2 squared times 2 squared times 3 squared times 20, which is 2 squared times 5. And so this is, here is 2 to the 4th. This here is 2 squared. This here is 2 to the 6th times 3 times 5. What's going to be the next thing? 2 to the 8 times 3 squared times 5 squared. Then 2 to the 10th times 3 squared times 5 squared times 7. I don't know, that might be the pattern. I'm not interested enough to find out though, so let's just pretend I just asked you, oh, fun for a fourth word. So, this means our y was equal to x to the r times the summation of a and x to the n, right? That's what x to the n plus r would look like. So this is x to the r, I'm thinking of r as 1 times a0 plus a1x plus a2x squared plus a3x cubed plus, and so this is going to be x times a0, which I can factor that out. A0 is x. It's going to be 1 plus a1 is minus a half. A2 is plus 12. A3 is minus 144. A4 is 1 over 20 times 144. So that's what that solution looks like. Notice we only have one arbitrary constant because I'm only finding one of the 2 linearly independent solutions. I'm finding the one corresponding to r equals 1. There's going to be another solution corresponding to r equals 0, but we kind of have to tweak that with the singular point situation, and I'm not going to that.
Would this have been any easier to solve with the method where we don't change indexes, or is it kind of going to be hard either way?
So, if we don't change it, let's actually look at it without changing indexes. So, let's say we repeat without changing indexes. Indices, indices, I'm going to just like redefine the plural of index. Like redefine indexes to be the plural of index. Like English people are like, you can't do that. You can't just make up a word. Like, all words are made up. Of course I can make up a word.
It's
all made up. Like who came up with the word index in the first place? Come on. It's like, well, actually, the word is indices. No, I defined a new word. Okay, so repeat. Without worrying about index, worrying about indices. Okay, so suppose I was given this. All right, prove that this is a regular singular point, blah, 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 all that good stuff. Okay, and I did it. Then I want to find a series solution. Then I'm going to multiply 3 by x squared because I kind of know I kind of want it to fit like an Euler equation in the first place. Then I'm just going to assume my y equals a series of a n, x to the n plus r, and I'm literally not even going to write what the substitutions are because it doesn't really matter to me. Technically, I know that I'm thinking of these as going from negative infinity to infinity. But because of that, however I shift, it's not going to matter, so I'm kind of going to ignore it afterwards. So, plugging that into this, well, I would use x squared y prime plus x y equals 0. This means I would have the series n plus r, n plus r minus 1, a n x to the n plus r, plus the series a n x to the n plus r plus 1 equals 0.
How do you get the second one?
And what I'm going to do is I'm just going to,
Why is that last one plus r, or plus 1?
because of the x.
Oh.
Wait,
Okay.
Yeah, y is that. So I multiplied that by x. So the power of x just bumps up by 1.
Oh, okay.
So why
And then this is x squared. If I took the derivative twice, I would have n plus r minus 2, but I multiplied by x squared, so the minus 2 goes over. And I have this. So I have that.
Oh.
Now what I'm going to do is I'm going to immediately shift here, n shifts to n minus 1, and then I'm going to actually just throw it all in one big series right away. Now, I'm going to set this equal to 0, and that's going to give me the recurrence relation. That is going to give me a n equals minus a n minus 1 over n plus r times n plus r minus 1. Right?
Yeah.
Now, we got to this point, we didn't shift indices. I'm actually going to write that down. We define indexes to be another name for the plural of indices. The index, or whatever. Okay, so, we get to this point, the problem said, hey, find the series solution corresponding to the larger root. What's the larger root? What's the r? So I get to this, I know what it is in terms of r, but I don't know which r I'm supposed to plug in. Here's where I just go do the shortcut. Well, look at that guy. R times r minus 1, there is no beta, the gamma messes up. That's it. So r equals 1, r equals 0, larger root is this guy. That's going to be what I do.
I like
It's like I'm off to the races, right? Like, just ignore everything. Let's just go fly by the seat of our pants. Hey, what about the index? I forget the index. We'll take care of it later. Yeah. When it gets here, I'm like, damn, we need that index. We need that. We need the R.
solution.
Just run back, just eyeball it, plug it in, just go up. Well, what's the theoretical percentage? You already know how to explain why you can do that if you're talking about math.
Would we never have to use, solve for the smaller root?
No, not in this class. There's a theorem I'll refer you to in the book that tells you how to deal with the smaller root, as well as if you have a repeated root, as well as if the roots are separated by an index value, an integer value. But I'm always going to ask you for the larger root.
This is a much happier solution.
Yeah, I guess. There's the smiley face one.
Yes.
So, try this one on your own. I will look at it next time. So, 3xy double prime plus 2y prime plus x plus 5y equals 0. Show point. Find the recursion. With the larger root. Assume A0 equals 1. Find the first four terms of the solution. I think this was actually from an old final. This is from spring 2011, problem 9. Okay, so do that. We'll pick up with that next time because that's going to take a while. In the last 5 minutes, let's just do some math for fun. We can do that. In fact, it's almost required. If you're going far enough into math and you can't do math for fun, it's not really gonna work out well. Some preliminaries to chapter 6. We're going to go into chapter 6. This is the last thing I want to do in chapter 5, so once we wrap up that example, I don't want to do anything. I'm going to talk about an integral transform. Of a function f of t is a function f of s given by transform or transformation. Given by big F of s equals the integral from a to b of some function kts times our f of t dt. Right? There are all sorts of integral transforms. There's something called the convolution functions. There's something called the Laplace Transform function, which is kind of what I'm segueing into here. But it's called an integral transform. A transformation, what is a transformation? A function is like a thing that takes a real number, outputs a real number. A transformation is something that takes functions as inputs and gives functions as outputs. That's called a transformation, right? So the derivative operator is thought of as a transformation. I put in x squared as an input, 2x comes as an output. So I don't really think of the derivative as a function, I think of it as a transformation or an operator because it's linear. It's a linear transformation. But transformations in general is just a function that takes inputs and outputs. There are also functions. So there's something called an integral transform where it computes a new function from an old function by actually doing some integral. You've seen examples of this. Integration by substitution is an integral transformation. I have one integral, the function is complicated, throw it in this magical formula, which is based on the chain rule, that's where integrated by substitution comes from, and it transforms it into another integral, which I call big F, and it's easier to deal with. You can do a lot of other things with it. Now, we want a transformation that generalizes power series. Power series were super nice, awesome, right? So sometimes if f is nice, we can write f of x as some series from n goes from 0 to infinity of a n x minus x naught to the n. This was called a power series. And f is nice just means it's infinitely differentiable, and the coefficients are such that if I do the Taylor formula for this guy, it still converges on some interval when I do the ratio test. It's kind of what makes sense. So the function is infinitely differentiable, and the derivatives don't get too big too fast. This kind of the very handy way to get about it. So e to the x is a function like that, sine of x is a function like that, 1 over 1 minus x is a function like that. We know a lot of functions like that. Okay. I want to do something better though. The problem is this sums over, well, n equals 0, 1, 2, 3. We want to make this continuous. What if I don't just want to sum over the integers? What if I want to sum over any real number? What would that look like? Create a power series, an integral. Okay, so I pretty much want to look at this as a function, as a series that doesn't depend on discrete values, right? N equals 0, n equals 1. But no, I want it to be work on anything. So change n to t, where t can be any number in 0 to infinity. It can be anything, right? I can sum over that, and yeah, so let x minus x naught, I'm going to change to x just to make it easier. And pretty much what I'm going to want is, yeah, so pretty much what I'm going to do is I want to transform this function into a new kind of function that's going to generalize that. And change the integral symbol, change the series symbol to an integral symbol over t. Right? So I go from n, switch to t's, make the summation continuous. We know that a continuous summation is just an integral. It's just another way to talk about an integral. And so basically now I want to sum over something that looks like this f of t times some function. Well, my function here is going to be x to the 10 dt. Okay, so now from 0 to infinity. So now I'm going to try to figure out what does this guy have to actually look like, f of t. So
Is it ST or T? You can change it. F of T.
f of t, I want f of t. Right, I'm just changing everyone. So the input values I'm plugging into this function, they would be like the ends, but I'm making the input continuous, so I plug in t's into the function, which means I put a t here, which means this guy, I will actually want to behave like x to the t, and making the substitutions, you get this. We want a nice way to look at this new function here. X to the t, kind of annoying. So I probably want to rewrite that. We're going to get the s later. This is an exponential function, right? Because dt is thinking of t as the variable. Can I rewrite this exponential something nicer? What's a nicer exponential?
e to the p natural log of log x.
I can write this as the natural exponential because that's the best one to use. Everyone knows this. So t ln x dt. And so now, I want to make sure that this converges, but I'm not a series anymore, so I don't have the ratio test. So I have to make sure it converges some other way to make sure we converge. For 1, I'm going to make sure that my x is less than 1 in absolute values, because then I know that this has a chance of converging if it goes down to 0 when I'm summing over infinity. So that's the first thing. So this means that I want my x to be operating between 0 and 1. So that this is just a fraction that's less than 1. As I'm raising the powers, it gets smaller and smaller and smaller. So I'm integrating over time, I'm integrating smaller and smaller things. So the hope is that will maybe make it converge to some smaller result. Then I can add some other stipulations here to make sure that we always get a real function. Because technically I can plug in a negative into the log and I get a complex function. But on top of that, force x to be greater than 0, less than 1, to get a real function. As in real value function, as opposed to a complex value function. You could actually generalize this to the complex case, but we're not going to do that. And then this would mean, what can you tell me about ln of x if my x is between 0 and 1?
It's negative.
It's negative. So what I'm going to do is set ln equals s, negative s, where s is positive, right? So I'm just going to think of the ln of x as some negative number. And so plugging in, we end up with the following. My big F of s is going to be, integral from 0 to infinity of f of t e to the minus xt.
Oh, so we just did a substitution, like.
We basically did a substitution where I replaced my x to the n with x to the t, let my t can be anything, and I rechanged that. And then I replaced the coefficient with just some function that I want to transform, and then I just kind of finagle things so that it gives me a nice value. Ultimately though, I end up with this special equation right here, which is, that is called the Laplace Transform. So basically, you want to talk about a Laplace Transform, basically what it is, it's like making a continuous power series. A power series that sums over all real values from 0 to infinity. This is called a Laplace Transform. Engineers love this. They're all over the Laplace Transform. To a math person, it's just another integral transform. What's so special about it? Engineers love this though, because why? It makes solving differential equations a lot easier. That's why I love it.
You got no biases at all, Jhevon.
Use it. We all have biases, yes. Using this function, which I'll show you next time, we can look at a differential equation and we can transform that differential equation into a polynomial equation. So I can actually use this function, I'll show you how we use it next time, and give me a differential equation, I can turn it into a polynomial. A polynomial in terms of the variable s, right? And then I can just solve this as a polynomial. And pretty much what we do afterwards is we take what's called the inverse Laplace transform, which means we take off the transformation that we had put on it to change it back to a function of x or t. And that's going to give us another way. But, so next time, we're going to finish up the example that I left for you guys. We're also going to use this thing to solve differential equations. And it's going to be pretty cool stuff. See you guys next time.